Good morning, everyone. Thanks for the introduction there. My name is Nick Tudor. I'm the CEO of a small company here based in Malvern, Worcestershire, called D-RisQ. I'll just share my screen, which I hope you can now see. So I'm going to trundle through this the next half an hour, 40 minutes or so, and we'll take some questions at the end, if that's okay with everyone. And of course, I'm talking to a camera, so it's very difficult to get the interaction, but I can see you on screen just about here. So. Right then, so without further ado, so this is about artificial intelligence in autonomous submersibles and some other systems. But before we get into what there's done for the actual vehicles, I'll give you a canter through what we do in order to be able to get to that particular point. Because you don't just magic up some AI and there it is. You have to put it into a system. So we'll talk about that as well. And I hope you're ready with your your pens and pencils, because there's some mathematics that we have to go through as well. Bet you didn't expect that on a Friday morning. Okay, so this is me. I was born in Hereford, which isn't too far away from Malvern. I went to Leeds University. I was sponsored through the university by the Royal Air Force, and I was commissioned as an engineering officer in 1986. And I worked on all the aircraft you can see on the picture there. The Air Force then sent me to go and get a master's in software engineering, which I did at the University of York over the millennium period, over 1999-2000 as well. So I've been there and done it. And then I went and left the Air Force in 2003 and joined Kinetic until 2011. And then I set up 3 companies. I've got a personal consulting company, a training company, and I then set up D-RisQ with 2 other partners here in Malvern. I've got 10 employees, and 2 of those have been apprentices at various levels. So I'll talk about that perhaps a bit later. And we build automatic verification technologies. And the idea is that if you can automate verification, then you can make things much faster and much cheaper through the development process of software, which I'm sure you're very familiar with. Recently, well, no, about nearly 2 years ago now, I was asked to be an independent panel member. In fact, I was the chairman of Total Energy. So that's Total. You may have seen their petrol stations around the place, but they're investing in quite a lot of things now. That's not just petrol orientated, oil orientated, and they've got this design authority, and I'm their independent chair. So with a few more bits and pieces like that coming down the pipe for me as well. So that's quite a quick canter through a number of years of my career. So entrepreneurship then. No, I don't drive an Aston Martin or a Lamborghini or a Ferrari or anything like that. My staff get paid before I do. So after 8 years, I started on a very small salary last year. I've invested many thousands of my own money into the company, and those are the 2 companies I talked about. So I work for those 2 companies, my own companies, and that's how I make an income. I regularly work more than 80 hours. For example, Tuesday this week was a 6:30 start, and I finished at midnight. And I work the weekends as well. I should be working this weekend as well. So for my holidays, it means both the phone and the laptop go with me. I'm not sure how well that goes down with my family. So the question you might be asking is, why on earth would anybody want to do this? Well, good question. I want to change the way the world does software. You may be aware of the cybersecurity industry. The reason we have a cybersecurity industry is because there's an awful lot of very poor software out there. And it's full of holes, and that shouldn't be the case. From my perspective, software is either a 1 or a 0. So it either should work or it shouldn't. And if you can't show that it works, why are we using it? And of course, what I'm really into is safety critical software. So safety critical means if it goes wrong, then there's going to be a bit of smoke, a bit of fire, a bit of screaming, probably more than likely to be some death. So the software has absolutely got to work. So if I can change the way the world does software, then maybe then I can make a few quid and I can get my Aston Martin. We'll see. Okay, so how on earth do you develop assured software? Well, there's a development life cycle, and it starts with a conversation with perhaps the client or the system owner, but you need to set out what it is you want this system to do, and that's called system requirements. And then what you do is you transform that through a software development process. You can use any life cycle you like. The fashion is DevOps. Some people use Agile. This is a waterfall kind of model. I've got some news for you. They are all exactly the same. It's just how you actually do the things that you actually need to do in a particular way. So there's no difference between any of the life cycles, spiral model, the whole lot. So you've got to transform somewhere in shape or form into some software requirements that's different to system requirements, which I'm sure you know. Then you go into do a design phase. Then you go into a coding phase, which the vast majority of people really want to do some coding. Well, it's not about coding. This is engineering we're talking about here. And then, of course, the source code gets compiled to the binary that sits on the processor. So that's called the executable object code. Well, that's great. That's all the very exciting forward development path. But what you've actually got to do is show that when the transformation has been done, that's been correct, it's been complete, nothing's been added to it that you shouldn't have added to it, and that's agreed with all the stakeholders. So that could be, in this case, between software requirements and system requirements. The system requirements owner agrees that what you've said you're going to do is exactly what he wants you to do. And then all the way through the process, you've got exactly the same backwards check, this verification check that needs to be done. And unfortunately, because it's software, we can't check that the ones and noughts are all exactly lined up in the right order. It's very difficult to read that. So what we also have to do is to say, okay, does that actually satisfy what we wanted it to do in the first place from both the design and the requirements perspective? So there's a whole series of checks that need to be done there as well. And the reason we do this is because we need the evidence for the safety case or the security case to show that, yeah, actually, there is exactly the right number of ones and noughts, and they're all lined up in the right order. And this is what they're doing. You have to read what they do in the requirements base. Now, from a safety critical perspective, the development costs, the sexy part, if you like, can be about 20 to 50% of your effort, and depends on how bad you are at doing this. The verification cost can be as much as 80%, and I've seen it go an awful lot higher. I know one program that had a $3 million budget to develop something, and they spent well over $60 million. So that's 20 times the cost that they budgeted for it because they didn't get this bit right. So I hope that's quite a salutary lesson for them. Okay, so what do we do in D-RisQ? Well, all those colors that just turned blue, we will automate those. So we are automating them, and that means we can make a considerable saving over the life cycle of between 60 and 80%, depending on where the benchmark is. So that's what we're all about, and that by doing that enables us to do things faster and do things cheaper. It also means we can do more complex systems as a result, because you've not got the project risks involved. So it starts with requirements. You may have seen this before. So suddenly a heated exchange took place between the king and the moat contractor. So what often is said at the end of the program, of a software program, is if only we had got the requirements right at the start, or if only we got the right requirements at the start. You can choose which way around you want the requirements and the word right, but that's often what happens with 2020 hindsight. So it all starts to go wrong if you've got the wrong requirements. Shockingly enough, you're implementing the wrong thing right from the get-go. So we need to be very clear about what we mean. So this is a quote from a very long time ago now. If the baby won't drink the milk, then boil it. So what are we going to boil here, milk or babies? And it's a computer, so it's got a choice to make. And from our perspective, it's kind of obvious, I hope. From the BBC website, it said after prison, he graduated from the University of California at Berkeley. He found it difficult to find work as a felon, so he became an electrician. So what exactly does he mean here? Does he mean that because he was a felon, he couldn't find work, or he wanted to find work as a felon? So it's a difficult one to pass sometimes. So to bring this into computer speak, and I'm sure you can work this out, depending on the compiler, the answer to why equals A plus B times C minus D is either 29 or 13, and you can work this out for yourselves. It's homework if you wish. So we have to be very precise about what we want this machine to do for us. Otherwise, it's going to cost us a lot of time and money. Testing then. So no doubt you'll be aware that there's an awful lot of testing that needs to be done, but unfortunately, testing only shows the presence of you having done something wrong. So I don't personally like the word bug because it's too cute and cuddly. It's you've done something wrong. You've made an error somewhere along the way. This is a quote from a computer scientist called Edgar Dijkstra. He's a Dutch mathematician, and he coined a term called formal methods in the late 1960s, and this provides the mathematics behind computer science. And software engineering is an engineering discipline, so it needs to have mathematics in it, like every other engineering discipline there is. Although that's quite a dry quote, what I prefer is perhaps this one. Those of you who are fans of Terry Pratchett may have read this, that Death in Hogfather, who talks in capital letters, the mere accumulation of observational evidence is not proof. Just because you've tested it a bit doesn't mean to say it's always going to do what you want it to do. And more crucially, that it's not going to do the things that you don't want it to do. And when we're talking about autonomous systems, that's why we haven't got autonomous systems out there. It's because we're quite frightened about this thing doing things that we don't want it to do. So why are we using mathematics? Because it's complex, and software systems are complex. There's lots and lots of information there. And frankly, it's more than we can really comprehend whole in one head. So we try to help ourselves by doing some modeling. And by doing that, we can then deal with that kind of complexity that's going on. And we do this in the natural world, as we do, you see perhaps the weather forecast. Behind all that is models that are being used to try and predict what's going on. From our perspective, because we're talking about a 1 or a 0, that's a number, we need to have a mathematical meaning behind it, or from our perspective, and the English for that is semantics, of course. So if we can have mathematically sound semantics behind it, then we can say that the model we've got is not ambiguous, it is unambiguous. And that's something from which we can move forwards. So do we really want to use mathematics? Well, why would we use mathematics? Well, abstraction, which we'll come to in a second, versus confusion, or you can get something precise rather than being ambiguous. And of course, we can reason about stuff pretty well, and that gets rid of doubt. Why wouldn't we use mathematics? And I can see one or two of you going, "Oh no, not mathematics." Maths is seen as difficult, right? And in this case, formal methods, yes, it is difficult. And in particular, one aspect of this is abstraction is rarely taught. And what I'm going to do is just talk to you about abstraction for a second, because it's important for what we're going to do next. So what do we mean by abstraction? What we're trying to do is to summarize something. We're actually going to look at the important aspects of what we're trying to reason about. So we take away all the information that's not relevant to what we're trying to do. We have to make sure it's the right information to take away. And then we can say, right, the information that's left, that's the important thing I'm trying to look at. So that's what we mean by abstraction, or précis is another way of saying it, perhaps if you do it in English. But we're trying to just focus on the important bits. So here's an example of abstraction here. When the first London Underground map was published in 1908, it had all the features of the geography. So the rivers were there, the distances between stations were there, and that was all done to scale. But the purpose of a map is to show the travellers the relationship between all the stations, where the stations are on what line, and the relationship between them, particularly things like interchanges. So unfortunately, the fidelity of this map made it difficult to extract the information that you need. So this is the original map. I don't know if you've seen this before, but you can see all the curves of the lines are on there, and there's the river. The distances between the stations is to scale. So you can see right in the middle here, next to number 4, there's 2 stations that are right next to each other. And that kind of thing was difficult. And of course, from an expansion point of view, when you add more lines, it gets even more complicated. So in 1933, that map was replaced by a much more abstract version called the diagram, and it just showed the connectivity of the stations. The surface detail was abstracted, the distances between the stations was removed, and all it gave you was the actual orientation of the lines as they crossed each other rather than the specific curves. And this is what it was replaced with in 1933. So hopefully that's a little bit more recognizable to you now, having seen perhaps the London Underground map as it stands now. Excuse me. So why is this useful? Well, it gives you a conceptual model of how we actually see the London Underground map, because we are underground. All we want to know is, do I get on at this station and get off at that and change to the next one? It allows people to make sense of what is a complex situation. You don't need that geography. You just need to know where you want to get to. And although this was done in 1931, it's been regularly updated, as we know, very recently to add, for example, Crossrail, and that's a program on which I've worked. The success is really down to two things. Firstly, it's an elegant presentation, and secondly, it's an appropriate, and that's the key word here, it's an appropriate abstraction in order to be able to allow you to do the things you need to do. And that's the kind of thing that we need to be able to do with all software. We need to take away the irrelevant information to focus on the things that we really want to demonstrate about our process. And in particular, from our perspective, we need to be able to do proof. So what do I mean by proof? Well, it provides us an insight into why something is actually always going to happen, or conversely, show that it's never going to happen. And that's a unique thing with proof. You cannot do that through test. So it could be completely informal, or it could be an English language thing. I'll give you an example of that in a second. The thing is that these proofs are easy to produce, but you have to basically review them and all agree that that's okay. We're looking for something that's a bit more mechanical. So we'll do that in a sketch in a second. That, as I said, are easy to produce or to refute. So this is something you may have come across before. So there's no test on this, by the way. You don't need to write this down. I hopefully you remember this from when you did your GCSEs. So a squared plus b squared equals c squared. Okay. How do we prove it? Well, this is a topological proof. So you can see, just between you and I, that at any time, as long as you keep that right angle there, you can vary the sides and the squares will move with it. So I can produce any of those. That's a topological proof. There are a number of proofs of Pythagoras. So what you don't need to do is to go and test it, because you don't need to do 3, 4, 5. Well, hey, it works. 6, 8, 10. Well, hey, it works again. Well, it should do, because it's twice the size of the last one. But 1, 1 square root of 2, it will still work. So you've got something here which you can now see that there is never going to be an instance where this never works. But if I was to add something else to this, like Fermat's last theorem, proving that there is nothing that meets Fermat's last theorem is the only way to do it. You can't do it through test. So a mechanical proof then, which is a fully formal proof, it gives you all the relevant information that you need in order to be able to undertake that proof. So the question really is, are you going to get humans to do this? Because this sounds really, really hard. And of course it is. So what we do is we use a machine. And in fact, myself and quite a few of my colleagues in a previous life, we did all the independent mathematical proof that the Typhoon flight control system and engine control software was correct. And there was nothing else in that software to make it go wrong. And that was done with tools that we developed ourselves, and then we use those tools to actually do that proof. Of course, it's independent on hand code. So they need to be accessible, and that's really what we're all about. So going back to this, if I can provide a model of every one of these artifacts in some way, shape or form, and I can bless those models with a mathematical semantics, so I can show you what those models mean, then I can use that in a mechanical way to automate verification through the use of proof. And I don't therefore need to do test. And as a result, not only is it faster and cheaper, I'm also very, very sure that the design artifact actually does do what I want it to do. So what do I mean exactly by this? Well, if I've got development artifact number 1 in language, so let's call this software requirements, and we're going to use the language called English, which I hope you're familiar with. What I'm then going to translate that to is something called a design. The next step in the process, we'll call that in a language called Simulink. So that's a human doing the design. That's a very human activity to be done. All we're going to do is to give both of those an appropriate mathematical representation in the same language. So in this case, it'll be a language called Communicating Sequential Processes, or CSP, and that enables us to do an automatic proof. So we can use that kind of process all the way through, using an appropriate language all the way through the design process. The impact is going to be something like this. So typically, if you use to develop an avionics system, for example, $20 million is not unusual for doing that. If you use one of our tools, we can cut that cost to between 25 and 33%. So that's $6 million that you don't have to spend anymore. And if you use the couple of extra tools that we've got, that will cut between 60 and 80%. It depends on the individual case. Right, so that's setting the scene for what we've done on our various projects. Assuring behavior then is all about trust. Why aren't we being driven around in autonomous cars despite the vast sums that have been spent around the world? And by the way, this has been going on in 3 massive waves of investment in AI. We're at the 3rd wave, and it's just tailing off now. There are companies failing all over the world because they've been unable to get the trust element in it. And for a good example here in the UK is James Dyson decided to pull out of the electric and autonomous car market last year because he couldn't see how he was going to get this element done. So why aren't we doing this? Well, because you need trust and you need a lot of money. So the cost to achieve trust is exorbitant. So, and the reason for this is it's not possible to assure the behavior of AI. Okay, so fundamentally, there is an issue at the root of everything that's been done with machine learning and with neural networks and the like. There is a great YouTube video on the link at the bottom there. By all means, go and have a look at that, talking about why we're not going to get to where we want to be with AI anytime soon. So what on earth is this artificial brain doing, and how on earth am I going to be able to say that what it's going to do, and particularly not do the things I don't want it to do ever? So what we've done is we've decided to cage the AI with some sort of predictable behavior. So it's a safety monitor, if you like. So we put it in this cage, it bounces off the walls. That means we can extract the behavior of AI, the good things about AI, but we know that it's never going to violate that boundary. So if we can define the boundaries, then we can put AI in the middle of it, and then we can just take over control, like if you're learning to drive, like the instructor does. You're sat next to you, and he will brake when, or she will brake whenever you're doing something that they don't like. So the idea is to, as I say, to extract the benefits from AI, but have the safety assurance as well. And recently, as I mentioned about Total, without prompting from me at a conference recently, Total has said, this is what we're going to do with all of our autonomous systems. So the approach to developing the cage then, this is just a little bit of an advert, I suppose, but we have the system requirements free form. They're written in English any way you like. And then what we do is we use one of our tools to define those cage boundaries. Using our tool Capture, including the never behaviors, including the failure, what happens when something goes wrong. And then there's a review that goes on with that. We then do the design in Simulink, and we do the verification of that using ModelWorks. And then we auto code that to C. Actually, it's a subset of C, it's MISRA compliant C, and it's got a formal semantics to it. And then all we did at this particular stage was do test. The 2 tools, Clause and Fever, aren't quite ready yet to do the verification of the source code automatically against auto-coded C, and then to obviously do the verification of the automatically compiled binary. So the point about doing all this is that it gives you evidence to comply with standards. And that's important because you've got to get to the regulator who says, yes, this is good. Maybe we'll talk about the regulator in a minute. So the projects that we've been involved in, firstly, the sort of scope of this is Innovate UK, which is a government, comes under the government business energy information, I think it's called, systems. can't remember what BAE stands for now, the business sector. We did maritime, air, underwater and land projects. This one was with the University at Surrey. Actually, it's for a vehicle that's supposed to go and roam around off planet. So things like the moon or that kind of thing is what they're shooting for. Surrey has got a good space sector in it. So what we also showed, based on some of the assured behavior of an individual, so we know that the individual is always going to do the things that we want it to do and never do the things we don't want it to do, we can now plug that into an arbitrary size swarm. So arbitrary doesn't mean infinite, because that would be daft. We're doing this as a very large swarm. We can assure the behavior of that swarm or show where the swarm will fail to behave, including if an individual fails to communicate or fails in some way, will the swarm still be able to achieve its task? And that's quite a large problem to crack, right? So this is the first project that we did with some form of artificial intelligence. So the yellow boat is has got no one on it. The blue boat in the foreground has got 2 people. Their job is to basically drive around the sea and drive themselves at autonomous boats or support them as they're going through. We're on board a small fishing vessel, that sort of size. I'm bouncing. I have got video for this, but unfortunately it's pretty poor. It doesn't come over very well on camera because I'm bouncing around in the Solent. So what this did was we drove, those 2 guys drove their boat directly at the yellow boat, and that got out of the way in accordance with coal regs. Coal regs are the collision regulations for sea, or the rules of the sea, if you like. What that means is that another sea user would expect the boat to have a particular behaviour because that's what they're trained to do. So this boat's also got to react in the same way. So that was successful. And then we said, well, that's great. That's 2 dimensions and pretty slow. Why don't we take it into the air? So we worked with a company called Cannon Lens, and in this case, we wanted to comply with the rules of the air, or CIRA, as it says there. We also added this behaviour of never happen as well onto it. So we showed that this must not do the things that we don't want it to do, and we had to define that. And we also looked at what happens when something goes wrong. So we had some failure information going into it as well. And we involved the Civil Aviation Authority in looking at what we're doing, and they were pretty impressed with what we'd done there. Obviously, in this case, compared to the previous project, Maritime on New Smooth, this is obviously much faster, and it's got 3 dimensions. And although we used quadcopters to do this, we didn't allow them to just stop. We had to continue with the, or stop and hover, we had to continue as if it was a normal winged aircraft. What we also did was we took a bit of the learning that you get, or training that you get as a pilot, and this is often missed out in people developing systems. It's all very well saying that the system's got to do this, but actually what you really need to know is what a human does with a system that you're trying to replace. So the pilot goes through an awful lot of training, and you'll be very pleased to know that if you ever get to go flying on holiday again. The pilot has an awful lot of training and has an awful lot of experience behind them. So we want to be able to take some of what we call the airmanship package, take some of that knowledge, put it into this package, and be able to say, well, this is what a pilot would do. So in order to test that out, we put it into some simulations, pathological situations that never really occur, and then say, well, go on, then get out of that, see what happens. And in every single one, they avoided everything they're supposed to have avoided with completely explainable behavior, which is great. And the statement was from pilots, that's exactly what I would have done, which is fantastic, absolutely fantastic. So the whole point about our part of this was to be able to say, well, we put some rules in here, the actual behaviors that we want. We can now tweak those as much as we like. So because it's just software, we can do that anytime we like, and we can add more sensors, or we can change the comms, we can have all sorts of things. Because it is just software, we can adapt this as much as we like. So well before something like yeah, this was not supposed to happen until the November, but in July 2018, Cannon Lens went flying. It was a nice sunny evening. The drone took off, went to point 1, and was supposed to fly all the way down here to point 2 in a straight line. Here we had a little beacon which was sensed on board, and the rule was to turn right, so it did, and the specifics of that was you have to make a distinct turn. So we said, right, you'll turn 90 degrees. So 90 degrees it does. and there's a safety bubble around the outside of the vehicle. There's a safety bubble around here, so extremely conservative about this. As I say, we can tweak these in and out as much as we like. And when it gets to a position where we say, fine, you can carry on going back towards point 2, it did that, but then it realized it's still within this collision risk area. So it did another avoid maneuver. So there's another 90 degrees here. And then when it's decided again that it completed that, that avoidance maneuver, it then carried on and went back to point 2. That was all static. This, I hope you can see the video okay, is airborne. So what you've got is 3 aircraft here. You're on board 1. Our software is on the one in the middle of the screen here, and coming at it is another one. And it's just sensed it, and it's getting out of the way. You can see people on the ground over here. There's some up by the cars, and obviously there's a person controlling the vehicle that you're on. And you can see it's maneuvering out of the way. There's a bit of wind that makes it a bubble there. And you can just see this little dot coming away to the left now. That's gone out of the way. So it's still doing this maneuver to get out of the way, but it's still within the collision risk zone. As I say, we can tweak this. This was the first flight trial that they did. And then around about now, it decides everything's clear. And there it goes back off towards that corner of the wood over there. And that's done completely autonomously in accordance with the rules of the air. And I think that was the first time that this has ever been done. It's certainly the first time it's ever been done in the UK. And that means that from another air user's perspective, if we can get the right sensor package on board, this will always behave the way another air user would expect it to behave. So we took all that learning and then went underwater, obviously much slower, but still 3 dimensions. This is A2I2, and we had 2 use cases in this. One to do nuclear decommissioning at Sellafield. There's some very bigger than Olympic-sized pools full of some very nasty material that needs to now be extracted. So that's at Sellafield. And we demonstrated to them in 2 stages, firstly August last year, and then just recently, a couple of months back, the final demonstration that we could do the kind of things that we said we would do on this. Very successful demonstrations, and we're now, I think it's next Friday, we've got the meeting with them to take this to the next step, which is actually put it into one of their pools instead of a demonstration. So what does that look like? This is the contraption. You can see all the people we were working with here. So Thais were just a little bit involved. National Oceanography Centre down on the south coast, Manchester University, obviously ourselves, Forth, and this particular programme was led by Rovco. This is Forth's facility up in north of Cumbria. So what you've got is 2 bits to this. You've got the lily pad on the top, which you'll see that in a second. There's a solar panel on top because many of these ponds are outside, so you can get recharging done onto the platform fairly easily. And then at the bottom, you can actually see the AUV, the autonomous underwater vehicle. So here it is being put into the test pool. This is a 6-metre deep pool. So the lily pad with the AUV underneath it is now trundling along. And that's getting into the centre of the pool. This is our final demo with Sellafield in the room. And unfortunately, I'm up against the side here. There's lots of people wanting to get video of this, but you can see the AUV untangling itself from the lily pad. There are no wires back to the side. This is all done through wireless onto that platform. There is a wire at the moment between the platform and the AUV. We're hoping to remove that. You can't do wireless communications underwater. Water blocks those kind of signals. So the real problem is, how do you communicate with these vehicles, or these types of vehicles? And we think we may have a solution for that through some work that was done with the University of Manchester by using light as well as sound. So the other part of the program was offshore. We did do some work on the Offshore Park. We've got an extension program to that, which we're on now, and we've got to do some demonstrations by October offshore, because nobody really wants to go offshore and do this in the winter, bouncing around in 10-metre swells. Not really that much fun. So this is a typical look at what you might see on a wind farm at sea. You've got the turbines here, you've got some sort of substation, all with cables underneath it. You've got the converter for AC/DC, and then another cable back to the shore here, and then going into the grid. The problem is that the sea actually scours away at all the infrastructure that's underwater. So we need to inspect it, make sure it's clear of anything that's fouling it, and that it actually is going to still be there when we want it to be there, because obviously, you know, there's no point generating electricity if you can't then use it back on shore. So this is a video of somebody manually driving an unmanned vehicle with on board a camera, which is done by Rovco, and that's got machine learning in it. So it is going to start looking at these things in various ways. What you're going to see is it identifying different objects, but there's another version of this now which gives us a three-dimensional representation. So it's not camera, it's a machine learning interpretation of what the camera is seeing, and it will be able to give a 3D rendition of that. I haven't got a video of that, but this is pretty impressive nevertheless. So let's just run VT. So what we're trying to do is to do this with no tether. So the vehicle will do it all on its own. You can see it identifying objects, and on the left-hand side, it's locating that on the map. I don't know why anybody would want to put a chair there. Perhaps they were interested in having a picnic, I don't know. But you can see these things have been logged on the left-hand side. So there's some machine learning identifying objects that shouldn't be there. And then it's being able to then go back and task to say, what do we want to do with it? So a human will go, okay, that's fine, or actually we need to send somebody down and do something with that at that particular point. So there's a whole extensional use of machine learning there. And it also applies to oceanographic science. So I mentioned National Oceanography Centre, so we're working with these guys. You may be aware that there was a competition a couple of years ago to name the new research vessel. It was eventually called the Sir David Attenborough, but Boaty McBoatface was put forward, and this is Boaty McBoatface. So the NOC named their underwater vehicles Boaty now, and that is it. So you can now say you've seen that. And our software is going to go onto these things. So that's the kind of things that we've been involved with. There's one last thing. So the future then. Yesterday I finished 7 days, 9 o'clock to gone 4 o'clock in some cases. Well, one particular day was 8 o'clock, staring at a camera just like this, working collaboratively with about 40 different people on and off in various sort of Zoom rooms that are set up. And we're trying to plan the next future, the next steps for the future of underwater autonomy. We're putting together some proposals that will spend, each of them will spend about 2 million, and we'll get some government grant to help us to do that. And these are the kind of companies that we're working with. So you can see some familiar ones, some obviously Rovco and NOC are on there, but it's everything from large organizations and actual brand new startups. So Signaloid is a startup spun out of Cambridge University. There's some research technology organizations like the Catapults there, and believe it or not, the Royal College of Art in the top right there. I'll be working with those. They've got because they do design, right? So they're interested in how to make these the design of various arms and such like much more efficient than the way they are at the moment. And we'll be putting those together. There are 6 proposals going forward to be then properly assessed and for funding, and we'll start in October this year if we get any of them funded by the government, and we will have them demonstrated within 2 years. So over the next couple of years, just for the underwater side, things are going to be quite exciting. In the air side, there's an awful lot going on in various areas, including the exploitation of things like hydrogen in the air and autonomy in the air as well. So there is a huge amount going on across the UK alone, let alone what else is going on across Europe and obviously into the US, who throw an awful lot more money at these kind of things. So as a summary then, what we're all about is assuring the behaviour of an autonomous and any other system as well, standard control systems. We're looking to make sure they're safe. We're looking to make sure they're secure. I've been involved in writing the standards for some of these. So for example, I've helped write software standard for civil aerospace called DR178C. What we're interested in making sure is we can comply with those standards, and in particular showing that the things that we don't want to have happen never will, and of course the huge complexity of combinations of the things that could go wrong, how we cope with that in a particular scenario. So that proof gives us that, and it's actually exploiting automatic proof. what we're trying to do is to enable the safe use of artificial intelligence systems, ML, artificial neural networks, etc., etc. We've got to comply with standards. Some of those standards are still being written, and again, I'm still being involved in those kind of things. So there's applications in all sorts of different autonomous system sectors, and there's plenty more to come with this. We are going to see the rise of the robots, if I'm getting a bit Arnold Schwarzenegger about this, the Terminator, but yes, there is definitely going to be more involvement of autonomous systems, particularly in the hazardous environment sectors. I'm not so sure, not that convinced that there is a market for things like in healthcare, etc., particularly social care, lifting robots, etc., because of the cost benefit side of life on that. So we'll see how these things pan out. If they become cheap enough, then maybe there's lots of places to use them. At which point, I'm going to take a drink and ask for any questions.
Okay, I think my video is back on. Yes, it is. Wow, I have to say, Nick, that I don't think I realised just how extensive the work that you've been doing really is, which is so, well, literally critical. Can I ask you, first of all, this is a question from me. We saw the autonomous vehicle on dry land and then in the water. I couldn't get an idea of the sense of scale. How big is it?
So it's about, that sit on the ground, it's about 4 foot high, and about probably 3 foot by 2 foot. So let's do that in metric. 1.5 meters high, something like that, and a meter by 1.2 meters.
I presume it's also exceptionally heavy. I mean, how do you get it in and out? Presumably a lift, or?
Yeah, there was a crane just disappearing out of view. Yeah, that just gets craned in and hooked off with a stick.
Hooked off with a stick. Excellent. How after all that technology, how non-technical.
Yeah.
I've got some questions for you. Some of the things actually that the students have asked, you've already answered, but there were some which I think which would be really interesting. How do you manage to get things up if they get tangled underwater, or do you just leave them there?
So the whole point about what we're trying to do is to make sure that they don't get into those situations. So one of the questions that's often put forward is that it's called the trolley problem, which you may have heard about, but if you haven't, I'll explain it. So the idea for the situation is you're on board a vehicle and something's gone wrong. Let's call it, there's a 38-ton truck coming in the way, and you're either going to hit the truck or you're going to hit the bus queue with all the grannies and the grandchildren in it. So you're going to die if you hit the truck. You're going to, or you're going to kill people. Or typically it's done. There's one person versus 3 people. Which way are you going to turn? Well, actually, the autonomous systems sector will have you believe, and that's what this is all about, is that situation will never arise, because the autonomous vehicle will have been able to foresee that's going to happen and will take defensive measures well before you get there. And there's all sorts of views of what happens with that going forward. So the idea is you should have been able to anticipate that. So when you go into the aerospace world, that is exactly what we try and do. We try and show that, this is without autonomous systems, of course, that we understand the context of use of that particular system to such an extent that we can say, this is what's going to happen. And therefore we can avoid the things that we don't want to have happen. A good example is the maximum ceiling of an aircraft is about 45,000 feet. What happens when you go to 50,000 feet? Well, it explodes. That's what happens, because the pressure inside versus outside, it will crack. Or the engines haven't got enough air to make them power them that high. So we understand the context of the use of these kind of things. So it should never get into that situation. Unfortunately, that's the probably not very satisfactory answer. But if you've done your job right, it should never get into that situation. If it has got into that situation, then something's very badly gone wrong, and then you're going to have to work it out from there.
I presume each situation you'd have to, weigh up each situation as it occurs. I will ask the question I was going to ask, which is also from Ash, was about solar technology. And the question was, the robot uses solar technology in order to recharge when it's below the surface. How would the robot effectively recharge if it has to do a nighttime mission?
There's lots of ways of doing this. In fact, one of those programs that we're hopefully going to be funded to do later this year, from a sea perspective, there's things called gliders. and the actual motion of the waves allows you to generate energy. So you can do things with solar, obviously, you've got a solar panel, that will enable you to start doing some recharging, and it's fairly low level. But with the energy harvesting, as it's called, you can use ways to actually generate your own energy. So you think about, just think about what happens when you go uphill. Well, something can roll downhill. And that is a way of actually generating electricity. And then, of course, you get on the other side of the wave, you can that weight will then be able to be used in another way to generate electricity. So there's all sorts of different ways of doing this. Quite a few years ago now, an aircraft was put up to about 65,000 feet, very, very light, massive wingspan, about the same wingspan as a one wing of a 737, I think, really big, but very, very light. That went up to about 60, 80,000 feet. Solar panels on the top of the whole wing, batteries on board, and it climbed and climbed and climbed under its own power.
Right.
During the day, it sat there. Obviously it needed engines to keep going, so electric engines with propellers on them, fairly slow turning, but it kept it airborne. And then at night, it just used the energy that it's got through the day, and it dropped about 20,000 feet. And then when the sun came back up, it climbed again. So it's above all the weather, and we'll do that. So there's lots of different ways around this.
Okay, that's absolutely fascinating. How long did it actually take you? I mean, you've described all the pre-processes that you have to do before you get around to any coding or anything like that. I mean, how long does it actually take you to come up with a concept in AI?
So take the A2I2 program, the one that we did for the nuclear decommissioning there. We spent quite a lot of time just thrashing out what the requirements were supposed to be, and then really examining what this thing should be, what the behavior should be. And that was not continuous time, but probably somewhere in the region of about 6 months.
Right.
Just kicking that backwards and forwards and backwards and forwards and making sure it was right. Nobody had ever done this before, as far as we were aware. And we didn't get it right. We didn't get it absolutely right first time. And that's the whole idea about using this in a mathematical kind of way, and with tools to help us. We went into the design phase, did some simulations, showed that was correct, or there were some issues, and then went back to the requirements. So we hadn't got into any of the coding at all. And then we went into the coding aspect, which is just an auto coder, because it's just press button, right? And then delivered the code, and that was then integrated. So that first demo last August, we started probably January the year before, and with everything else that was being done, with the camera being developed and the integration of all that onto the platform, took about 18 months, I guess, something like that.
That's a long time.
That was just to get the first step done, yeah.
But you have to be thorough. I mean, you made it very clear that you have to be very thorough about what you do. David also asked about specific programming languages. What sort of language? I mean, you mentioned C when you were talking. Is there anything else, or is it just C?
So the reason we used C is because it's widely used in embedded systems.
Right.
It gives us all the features that we need. We don't need to use every feature of every language. That's just there for fashion's sake. It's got a subset which we could give a semantics to, which is a formal semantics, a mathematical semantics. We also, as it happens, got a formal semantics for C++ as well, but we don't need to use that. We need everything that we've got. We need with C, and that was built on some research I did just after. Well, I managed to land, actually. I bid for the work and got it. The team did the work, not me. Years and years ago, back in about 1980, 82, 83, 84, something like that, there was a language called Ada. That was the fashion, particularly through the military in those days. And they put a formal semantics to Ada in that time, using the language Z to do that. And literally, it's just a Z. And I thought, well, all they've done is subset the language to a deterministic subset. So why can't we do that with any other language? And in early 2000s, that's exactly what we did. We picked up MISRA, which is standard sort of guidance from the motor industry, which is a good subset to use. All the guidelines with that, and then we said, right, can we implement that in some way? Get down to a subset of C, which is useful, and give it a formal semantics, which we did, which we've done. I mean, we've got the independent proofs of that. And that's why we use C. But we also use a functional language called Haskell. And again,
Haskell.
Yeah, it's not very often taught. I know that. The reason we use it is because it's got a very good tilt towards formal methods. So there's a mathematical meaning behind it. That again, I come back to you can write English and you can write code that's completely ambiguous. I'll give you an example about if the baby won't drink the milk, then boil it. You know, so what's the subject of the sentence here? Well, the same is true of programming languages, and you know, Java and all the latest sort of programming languages like Rust and what have you out there. I've all got issues with them associated with the way in which the compiler interprets the language, and it's the compiler that's doing that interpretation for you. So it's doing things. We went to see some people who were very heavily involved in doing some interesting cybersecurity work quite a few years back, and they said, well, why don't you use C++? And I said, well, if you change one line of code in C++, the compiled image can be completely different. You have a completely different runtime, maybe have a different behavior than the one you expected, what you had from before, just by that one tweak. Lots of other behaviors, because the compiler goes, oh, I can optimize that in this particular way. And that invalidates all the tests that you've done beforehand, and that causes a lot of time and expense. So why wouldn't I use a deterministic language like C? And as it happens, that both the project manager and the program manager, so the program manager is the one with the money, the project manager who is running it, turned to the techies and said, is what he's saying correct? And he went, oh yeah. I think it was a very interesting conversation shortly after that about why they were using such poor programming techniques. And from an industry perspective, that's what we really need to have. We need to have really understood programming, really understand what the language is doing, and not to do all this, you know, I've got a feature here, I'm making it really complicated, nobody can understand it. You've got to be able to use the tools available to us to be precise. It has got to end up with being understanding this is a 1 and this is a 0, not maybe they're all in the wrong order, or I've got more than I need. And again, from an aerospace perspective, we've got we spend an awful lot of time, an intense amount of money looking at the way in which people program. I'm in the middle of an audit now myself on a very large program, looking at their software and their hardware and making sure that this thing is only going to do the things that we want it to do, and it will never do anything that we don't want it to do. There's plenty of examples. The Toyota example, that the autopilot, the cruise control. There's plenty of examples there. That was built on software that had been changed with poor programming practices, and the particular instances where cars crashed and maybe people died because they couldn't disengage the cruise control. It's because of these kind of bad practices. And we need to get over that. That's got to be unacceptable, and that's what D-RisQ is trying to do. So there's a better way of doing it.
I have to be honest, I didn't know that there had been issues with cruise control, and that's going to make me think twice about using it next time I go out. So I wasn't aware of that at all. One of the things that you did mention, and Freddie actually asked the question about autonomous systems to come. So you already said some of the things that you're working on. What other things are you aware of in terms of autonomous systems that you think might come in the fullness of time? Be a bit of a predictor.
So there's plenty of wacky ideas out there, some of which will come to fruition, I've no doubt, but it's people trying to do autonomous kitchens, and I don't quite get why we want to do that. Again, if you want to spend £500,000 on a machine, great, because that's what it's going to cost you, but you've got to get a return on that investment somehow. And that thing needs maintenance, which still means people has got to be there to do that. So you're not removing the economics of it. Don't add up for me. I don't quite get how that works. Similarly, as I mentioned, you know, there's been people talking about robotic assistants or exoskeletons on social care staff being able to lift patients out of beds and all that sort of thing. Well, yeah, but they cost a lot of money. These things do cost a lot of money. So where's the economics of that working? Again, it needs maintenance. It will need costs, and you'll need people to do that. We're definitely going to get some systems operating offshore. That's without almost a shadow of doubt that that's going to happen in various ways. But the key to it is at the moment, a lot of these systems have got a tether to them, so umbilical down to them. We're going to have to remove that tether to enable them to do the things that we really want them to do. In airborne, there will be some. I'm not convinced by the Amazon delivery of the drones landing on your front lawn to deliver a parcel. Again, I don't quite get that. But there will be some aspects of that going on, I'm fairly sure. But it comes down to making it safe. So I'm aware of companies that I'm talking to who are doing trials. So, for example, the trials you may have seen going to the Isles of Scilly, down to the Isle of Wight, and out up in Scotland as well, out to Mull, where they deliver parcels. But none of those have got the assurance on it. They've been given very clear, delineated airspace. No other people are allowed into that airspace. In order to make this generic, in other words, make sure that any air user can have access to that airspace while this drone's going backwards and forwards, that's got to be seen to be safe. And we're not going to lower our guard in any way, shape or form for manned aviation to allow these things to just run around like uncontrolled missiles. And that's what we want to try and avoid. My passion really is to enable those things to happen, but and to mix with what we've got out there already with manned aviation, be that in a Cessna or whether it's in an A380. So.
One of in terms of AI, one of the news articles literally in the last week, they had, and I'd never seen this before, and I was quite fascinated by it, is there a guy who's paralyzed, completely paralyzed, and they've managed to hook up his head and his brain, and he's thinking words which are now appearing on screen. So the AI is actually trained to read his brain patterns to allow him to speak. Now, those sorts of applications of AI, do you think there's going to be more?
Oh, absolutely, yeah.
Right.
In places where we're prepared to spend those kind of money, absolutely they're going to happen. And they're being used in cybersecurity. But I'll go back to, so one thing I haven't said, that artificial intelligence, it's not artificial, it's not intelligent.
Okay.
I met somebody who a couple of years back out in New York, works in our consulate there. He did his PhD on this, and what he showed was when you train machine learning or whatever it is you're trying to do here, you as the human choose what it's being trained on. So that's the human, right?
Right. Okay.
So the selection of the data sets that are used to go into that is a human actually deciding what it's going to be trained on. And there's plenty of examples of where that selection of training in the data set's gone madly wrong. So, for example, Microsoft, tiny little company, you've probably never heard of them before, but they did do a release onto, I think it was Twitter, to try and mimic how people use Twitter. I think it was Twitter. Forgive me if I got that wrong. And within a couple of hours, had to remove it because it learnt all the bad things and it was being very rude.
Oh dear.
A lot of other things as well. So the training data sets is absolutely crucial. That's selected by a human, and it's not intelligent because of the way in which it works. It's dumb. It is a 1 or a 0 at the end of the day. It's not got that human creativity aspect to it. So it is not artificial and it's not intelligent. It's human. And it's human.
Interesting. Good argument. I'd like to invite the students, if anybody's got any more questions. I've got one more question as we end, but is there anything else that you would particularly like to ask?
Okay. David is asking if you do any apprenticeships.
Right, okay.
That was your last question, I think.
That was going to be my last question, so thank you for that one.
Right, so I mentioned we did some apprenticeships. We've taken, I've got this, if I can remember, we took one lad in and took him through level 3 and level 4. He's now moved on, and that's absolutely what you want to see. If it's not right for you or you want to go and do something else, by all means do. At the end of the day, an apprenticeship is for the individual, and if the company gets something out of it as well, that's really good. And if they want to stay and they're offered a job, there was going to be a job offer for this lad, but he decided to go somewhere else, and that's absolutely fine. His personal circumstances dictated that. I've got a young lady at the moment. We took her through, I think it was the level 4 for her, and she's now she's just finishing her 2nd year. She's getting firsts at degree level apprenticeship, so level 6.
Right.
with Coventry University, and she's doing exceptionally well. We're really pleased with her. She'll get another pay rise come her third year, and then she'll be offered a job if she carries on, and then she wants it in a year or so's time with a graduate salary. That's what she'll get.
Are they presumably software development apprenticeships, or
Yes.
are they something else?
Yes, they are. We've looked at other apprenticeships, but we haven't found any candidates that were useful for us. For example, in marketing. So
I'm gonna really put you on the spot now, just because my last question has already been asked. When you actually recruit, what sort of personal traits do you look for? I'm not thinking about in terms of technology.
really
I'm asking you in terms of how you would expect, you know, a potential employee to, in terms of behaviour, transferable skills. What do you look for?
Okay. So top tip, ladies and gentlemen, if you haven't done your homework before you get to that interview, because obviously to get to the interview, then you're out. You've got to get me at hello. You've got 10 seconds to get me at hello. Firstly, from your CV. You know, if I read your CV and I just put a spelling mistakes or whatever, you're out. Okay, because we get lots of these things and you're gone. So it's got to be good. When it comes to the interview, I'm looking for somebody who understands what I do, what my company does, and to be able to tell me that that's what it does, tell me that they've taken an interest in what we do. I've seen so many young people come in and they just want a job. If they just want a job, there's plenty of those going at the supermarket. I cannot afford to have anybody who doesn't want to be engaged with what we do. We're a small business. So do your homework. If it's something that you really want, then you will do that and you will get that message over to the employee. From there on in, it's yours to win, as opposed to you've already lost it. So even if you've done all your homework and you're really passionate and all the rest of it, there's no guarantee that you're better than another person who's done the same kind of thing as yourself. So give yourself the best chance, do your homework, get in there, do the research, find out what, for example, if I asked people what DR178C was, none of them have come to me so far and understand what that is. And it's the standard I held right, and it's the standard that's keeping you safe when you go on the holidays, because it's the software on board the aircraft is all developed to meet that standard.
Wow.
So it's absolutely crucial to us that people have done the understanding. They may not understand what DR178C is, that the detail of it, of course, there's a lot of, but to be able to say, oh, that's the software standard for civil aerospace, oh, big tick, thanks very much, And do your homework on the individuals who are going to be interviewing you. So who owns the business? My details on there. LinkedIn is there. Go and find out what stirs me. Go and see what I've been posting. Go and see some of that stuff, so you can reflect that in the interview and say, oh, I see you've been doing some work in autonomous vehicles. That's really exciting. Can you tell me a bit more about that? Or I see you've done this. Not tell me more about it, because it ultimately is you to say stuff, not me to say stuff as the interviewer. So that's what we're really looking for, and I hope that gets. It's not just me saying this to you. I hope there's people in your college, at Priestley College, telling you this as well.
I think the thing about LinkedIn is becoming increasingly important, to actually make connections. And of course, you as the employer can see that someone who is being recruited potentially has looked at your profile. So it actually demonstrates that they're interested as well.
Yeah,
so,
I don't have time to do that.
You do. Well, I have to say, if you're already working those excessively long hours, I'm not entirely sure. I'm surprised. So as we end, is there anything else anybody wants to ask? Okay. Well, in that case, thank you very much to the students of Priestley College, and thank you very, very much indeed to Nick Tudor from D-RisQ.